Good evening, everyone. On today's Math Club Talk, we have Shankha Suvra presenting on cutting the cake in n raised to the power or n steps. His main interest include graph theory and combinatorics. So I am handing over to him.
Yes, thank you very much for the opportunity for being able to give a talk. So today basically we'll be talking about cutting the cake in and titrated to the 6 steps. It's a very strange title, I'm aware, also on Pi Day. First of all, before we start though, I would like to thank Shubhajit for helping out in the arrangement along with Siddhartha and Shopanno, without whom all of this would be supremely delayed. So with all of that sorted, let's get started. So this overall talk shall be covering the Aziz-Mackenzie theorem, which was proposed or which was released in 2016, which states the following. After which we shall discuss some of the concepts required in fair division, which is a subset of computational social choice theory, to understand what really this theorem says and how the approaches and procedures work. After which we will have a nice epilogue at the end to kind of round up all of the observations and ideas and moving forward. So let's get started. So this is the main theorem, which states that for any n agents, there exists a discrete bounded protocol that finds an NV-free allocation of a heterogeneous resource, aka cake. Specifically, the protocol terminates in at most n tetrated to the 6 queries. Now, there is one clarification I would like to add, is that in the preprint at FSTOC 2016, they had mentioned this particular result of tetrated by 6. However, later on they came out with the paper which while having the exact same protocol with some very minor adjustments, they were able to get it down to the result of n tetrated to 3 times, that is n to the power of n. However, now coming back, as you see, this is a bunch of mumbo jumbo terminology. As we can see, it's very hard to follow. So let us first start off by defining what the definition of a cake is in this situation, or what a heterogeneous resource means. So cake is defined as a divisible heterogeneous desirable good in this sense. That is, that a good is something that we desire, we want to have more of, every single agent, every single person wants to have more of, and it is divisible, that is, it can be infinitely divided. So we will try to model it using an interval 0 to 1 in this case. As I have said, mathematically we map the entire cake to the interval 0 to 1, and it is heterogeneous in the sense that, as you might see upcoming, that every single cake that you have is not the same slice. For example, this you can divide it easily into multiple portions for everybody. Everybody gets an equal slice if you do the angles correctly. However, in this cake, say somebody is deathly allergic to cherries, then in that case they do not want that. That is heterogeneous in that sense, that not everybody wants every single slice, not everybody can have every single slice. So that is the definition of heterogeneous and divisible heterogeneous desirable good. Now, one thing that I will define is, a piece is defined to be a subinterval or a union of disjoint subintervals within 0 to 1. The reason we map it like this is because of the fact that it is a very easy mathematical model to follow, and we can map this to an arbitrary cake. Say you have any circular cake, which is in most cases, you will be able to see that we take the center and we can partition the cake into angles by making cuts, right, from 0 to 2 pi, and we can scale it down to 0 to 1 without any issues, right. So now one thing I would like to talk a bit more would be about divisibility. What does divisibility mean here? Because that will be a very important concept in the discussion of this overall field. And the first thing is that we assume in this talk we shall be assuming that a cake can be infinitely divided. So in real life, when we talk about cakes, really we have a knife, we cut the cake, and we lose some certain portions of it. However, for a simpler mathematical model, we use the fact that it can be infinitely divided to at least have an ideal case situation, right. However, it does not mean that the cake always needs to be infinitely divisible. For example, you can have finitely divisible goods. For example, say I have a bunch of gifts which I want to give to my friends, right? So I want to do it in a way so that I can fairly divide them. The concept of fairness will obviously be explained soon. However, for now, just assume that we are trying to have a certain benchmark for fairness, right? And we want to divide these finite number of items which we cannot divide. We cannot divide a car. We cannot divide, say, say a toy or say Beyblades. We cannot divide those and give it to people easily. However, in this talk we shall be still primarily be discussing about the infinitely divided case. Also, another side tangent I just wanted to share, it's not that relevant here, is the idea of goods and bads. Goods and bads are basically terms we have taken up from economics, because computational social choice theory has its roots in the study of economics, game theory and social choice theory in general, in which computer scientists later on entered the field and started working on problems. Alright, so goods are basically desirable items and bads are undesirable items. So everybody usually wants more goods, less bads, and that is why we can call them to be a maximization and minimization problem respectively. Now, coming back to the images of cakes as I have presented here. So say I have two cakes and say I have three people I want to divide it amongst, right? So in that case, how would you divide it? Or even more of a point is, as I had previously mentioned, that say somebody is allergic to cherries, right? So in that case, wouldn't dividing this be a bit more difficult than dividing that? Because that we could easily slice into 1/3 parts. We just take the cake, we slice it into 120° and 120°, 3 portions, and we are done. However, this is not that easy. But before we try to say, before we try to divide the cake according to fairnesses, we need to understand how do we quantify this understanding of, okay, the guy cannot have cherry, this guy cannot have the chocolate piece, or whatever else we have. We need a way to quantify that, for which we come to the notion of valuation functions. So, as I said, each agent has their own preferences, as evidenced by the previous slide, right? Now, we need to discuss each agent's subjective evaluation of various slices. That is our aim. So we quantify it using a valuation function. Okay. Now, obviously, again, depending on the cake we are discussing about, whether it is finite or finitely divisible or infinitely divisible, we will have two valuation functions defined. However, I will first of all start off with the definition of valuation function for divisible cakes. So what is it really? It is basically something subjective to an agent I, right? So let us start off with that statement that for an agent I, the valuation function represented by Vi is defined as a measure over the interval 0 to 1 satisfying the following axioms. Now, we will get to the axioms later, but is everybody aware of the idea of measure here? Okay. So even then I will still just mention it once. It is a way of trying to assign sizes to the sets in our context really. That is the main idea we are really going for here. In fact, you can technically try to think of it as a resultant from a probability distribution because of this second property, which is normalization. So let us just first of all go over the points. So every single piece of the cake needs to have a non-negative valuation. So every single piece, you cannot have a negative valuation of a cake. I know these are very obvious statements, however, it's best to keep those clear. Normalization is basically that the entire cake is valued as 1 for us, and if we have two disjoint pieces, then the valuation is additive. This property is a major assumption for the field of fair division. However, it can also be, we can also try to model different scenarios. An example of that would be, say we have a pair of shoes, right? So in that case, if I give you a left like a shoe for your left foot but not for your right, or I give you a foot for your right leg and not for your left, then in that case the value which you get is going to be very minimal compared to, say, I give you an entire pair of shoes, right? You can wear both of those. So those valuations don't really add up. Those valuations are not additive in nature. So this is a major idea which we actually, a major assumption which we work with, because it is highly relevant for our situations and also makes our lives a lot easier. Now lastly, coming from the divisibility aspect of a cake, we have the property of divisibility, where if we take any arbitrary piece x of the cake and we take any fraction belonging to 0 to 1, it can also be 0, yes, then in that case we can take a sub piece, a subsection or a subset of our piece of cake, such that the valuation of that would be that fractional multiple of the value of the entire subset of the cake. Yeah.
Why is it? What does fraction mean? Then you could have just said it as a real, right?
Yeah, we actually can't, because we are normalizing it, right? So it needs to be bounded from 0 to 1, right?
And any fraction lambda, so like does the word fraction was
I mean, what I mean to be like fractional as in like 0 to 1, that is what I meant to say. Yeah, proper fraction.
so it's a rational, right?
I mean, not necessarily. We can also say it can be rational. Yeah, it can be any value. Yes, like fraction. Usually, when we are using those terms, we are not necessarily sticking to the rationals and all that, but rather we are just, yeah, we are just mainly just mentioning that it is less than equal to 1, it is greater than equal to 0. Okay. Yeah.
How do you map the cake from being a cake to the interval 0 to 1? Is it some topological
I mean, there are two approaches to the like the process of cutting a cake. So one is that which this is a simplified version of, that is that we take the center of the cake, we assume it to be a more or less a circle, and we take the center and we can make slices from the outside to the inside, right? So we cut it accordingly. So in that case, the area will be determined by the angle made at the center between the slices. So the total angle in that case would be 0 to 2 pi, and that we can normalize. Now there is another approach which I actually wanted to go over, but I do not think will be able to go over because it has a lot of reading associated, and I also couldn't really complete it too much. But the gist of it is that there is also a topological method of studying or dividing cakes, which would which would not necessitate this cutting from the center. That would basically involve from what from my limited reading understanding, that you try to approximate the cake using simplexes. Simplices, like you take simplex and you try to approximate it from that. Yeah.
It's necessarily circular, right? Like we can consume a rectangular cake and then we can send 0 to 1, and then like it is more easy to visualize.
I don't quite follow. Could you repeat?
Is the cake necessary to be a circle?
I mean, not really, but since we are like as I said previously, that we are talking about the cake being the mathematical interval from 0 to 1. Now if you want to,
If we take a rectangular portion of the cake,
yes,
I think that is easier to visualize as 0 to 1.
okay, that also is a valid idea. Yes, that we take a rectangular cake and we can cut one side. Yes, that also is perfectly fine. Are the points clear here? Right. Okay. So I also defined the valuation function for an indivisible cake just for the sake of completeness, which basically states that again we have all of the same requirements almost. However, one thing that changes is that instead of going from 0 to 1 and trying to work with a measure, we have a set function, that is it takes from a power set and it takes it to real numbers. Actually, to be precise, it takes it to 0 to 1, because again we have the normalization criterion and every single piece is greater than equal 0. And lastly, we also have the additivity property, as I previously mentioned, that is very important. That is also modified accordingly. So if I have set S, which is my goods or cake, then in that case for every j belongs to S, we can take that as a sum, like sum of the valuation of j individually. Alright.
How do we do the summation of vi inside j?
So basically Vi of S is basically defined as, so I have fixed an I. So this is, I have a particular agent I. I'm talking about their valuation function, how they evaluate pieces of the cake. So we have Vi of S. S is a subset of the, like, S is a member of the power set of C. So in that case, for every single item that belongs in S, there is a valuation attached to every single item here. It's finite, right? So since all of these individual items are disjoint in nature, we can add those up, and that will be the overall total valuation of the set. Does that make sense?
Yeah, but it's like BIC only. If you just keep on adding up,
What?
it is becoming equal to BIC only.
No, I am iterating over J belonging to S, not J belonging to C. It's my, like, I'm if I take VIC, then in that case it would become 1. Yeah, fine. Yeah. Lastly, dealing with people's subjective ideas of valuation is not always, what just happened, not always the easiest to do, right? Because first of all, people aren't exactly able to always quantify their preferences, and second of all, we have the issue of not being able to deal with, like, 0 to 1 is an uncountable set, right? It's very hard to necessarily always have a nice valuation function that is easy to remember, easy to put in a computer's memory. Like, it's not always that easy to work with, right? So for that reason, Robertson and Webb in 1998 came up with this Robertson-Webb query model, which required you to not know the people's subjective valuation functions. You can only query them. So instead of trying to work with the valuation functions directly, you have 2 ways of interacting with them. That is what the major idea is in the Robertson-Webb query model. Alright, so as I have also written, is that a fair division algorithm is only allowed to interact with the agent's valuation functions via 2 specific types of query for the ith agent. Okay, one of which is the evaluation. So I take any subset or any interval from 0 to 1, and I can ask the agent that, okay, how much do you value this particular subset, right? And then the other idea is of cutting. That is that actually I should probably emphasize a bit more on the mathematical aspect of it. Is that, say if I have an evaluate query, first of all, then in that case ei x comma y is going to be defined as the value of vi x comma y interval. Okay, so like, is that clear? Like, if I'm confusing you guys, just let me know. And the cut query is basically that I have like, I have one starting point and I have a valuation, so I want to say where does it end. Okay, so it's kind of like I have x, I have alpha to be the valuation, and then I use the ci x comma alpha, that cut query, which returns me a y from x to 1 such that e of x comma y is alpha. Basically it is a sort of getting one parameter from the other, right? So we fix the first thing, we know how far we are trying to go, and the cut query gives us the end point. Instead, and in the evaluate query, we have the starting and the ending points, and we get to know the value of that. That is the major idea here.
So, do
Yes.
these queries help the computer approximate the valuation function?
What?
Do these queries help the computer approximate the valuation?
No. So the thing is that what the computer really does is that it asks the agent directly that at every single step, do you like this? Like, evaluate, would you prefer this one or this one? That is the evaluation. Or cut is that, like, I have this piece, I want you to cut it in half.
So you basically start from x and then you just go up towards 1, that up to how much if we go.
Yeah, how much till you get alpha, like that value of alpha. So if it goes up to 1, then like x to 1, if it is alpha, then you will get 1 as the result.
If x to 1 it does not reach alpha, then we will get 1 because we can't do it.
Yeah. Yes. So like the major ideas, in fact, like we'll just come to it right now, which is the idea of I cut, you choose. I mean, before that we'll need to define fairness. However, I'll just mention this. This is one of the simplest fair division algorithms ever. and it is also the oldest one. So basically it deals with the n equals 2 case. So say there is I and there is some other person, right? So then we are trying to divide a cake, like divide the cake equally. So what we do, we say okay, agent 1, or say it's myself, so I'll cut the cake so that it is half. So I'll start from 0, I'll do the cut query and I'll get the point till where I get the value of half. So I cut it, so both of the cakes have same value to me. So now the other guy can choose that one of them will be better than the other or equal. So if the other person says that okay, I have P part 1 and part 2, and that guy finds that okay, so both of the values have same, like both of the cakes have same value to me, so he takes one, I take one, we are happy. If in the case that one of them is less value and the other one is high value, they can take the higher value one for them and I can take the other one, because to me at least both of them are same. Make sense?
Basically, the queries are the actions which will take place in our algorithm to divide the cake, right?
Yeah. Divide or select? Like select a subsection or?
So actions are sufficient for.
Yes. In fact, we shall be dealing with this a lot in the Aziz Mackenzie case. If you see, there is a lot of slides there. So now that like the idea of the Robertson web query model is understood, right? Yeah. Because it will be a bit important coming on. So now before we get into the final envy free and all that discussion of how what fairness, like about all of the algorithms and everything, we need to first define what fairness is. So there are two major types of fairness when we are trying to talk about continuous cake cuttings. So the first one is proportionality. So say if I am the ith agent, then in that case the cake I receive is 1 by n, like is better than or equal to 1 by n of the valuation. So as in that if everybody had an equal division in my eyes, then I would have gotten this or worse, essentially. Got it? So that does not necessarily mean that it is envy free. Now this idea is going to be a bit complicated, so I'll just define envy free first, then you'll understand what I'm trying to distinguish here. So envy free allocation is said to be that I have one piece, another agent has another piece, so I would never like to get their piece instead. So I like my piece like I have it. Okay, that is what it means. So no agent prefers another agent's piece over their own. So out of all of the pieces that it has been divided into, this is the best piece in my eyes. Does that make sense? I see a bit confused faces here.
I mean, yeah, it does. Right?
Okay. Now, like just going back again to proportionality, because I don't think it made a lot of sense to you guys. Again, I'll repeat, is that like let us say I have a cake. Okay, I'll just re-explain this. So let us say I have a cake, right? And say I was the one dividing it. So in that case, how would I divide it? I would divide it into 1 by n, 1 by n, 1 by n, so on, right? N agents, n pieces, easy. Now, by that logic, what would I say I am entitled to? I am entitled to 1 by n, like a cake which is worth 1 by n in my eyes, correct? So proportionality means that every single person, the slice they get is valued greater than or equal to 1 by n in their eyes. That is what it means. So I got a piece, he got a piece, he got a piece, all of us got a piece, and we think that okay, us three, mine is 1 by 3, his is 1 by 3, his is 1 by 3, are subjective eyes. It is possible that I like his more. It is possible that I say there's Onjon sitting here, I like his piece a lot more, I value it at say 1 by 2 instead of 1 by 3, and I say prefer Kinshuk's to be 1 by 6. That is possible, but by the idea of proportionality, that would be a proportional level of fairness. So obviously, as you can see, that envy freeness is a stronger criterion, which I'll just prove as well. So we have, say I have like an envy free distribution, so it will also be proportional. Not too difficult to have proof. So say I have an envy free allocation, and then that would mean that for every single agent I, like ith agent, I would have VIAI being greater than like Vij, so my piece is better than everybody else's in my eyes, right? So now I can take a sum over all of the j. Okay, so what would I get? This stays the same because this has no j's, so this times n times vi ai, and this one is a sum over j. J is all of the agents, so that will be vic, which is 1. So n goes down greater than equals 1, and then we are done. Very simple proof. But however, proportionality does not imply NV free, which is why I was mentioning that NV free is a stronger statement or a harder statement, which is this. As I previously said, that every agent receives a slice, they evaluate it to be 1 by 3 in their own evaluation functions. Agent 1 say desires the topping on agent 2 slice, evaluating it at say 3/5 of the cake's total value, while the agent 2 evaluates that particular slice they got to be 1 by 2, the others is to be 1 by 4, 1 by 4. So agent 2 will not want to let go of his piece, his or her piece, and agent 1 would prefer the other guy's one more. So it is not envy free in a sense, right? Agent 1 is still envious of agent 2 in this division of cakes, and that is why we basically, like, this is a counter example to the fact that if, like, of proportionality implying envy free, that is all that is. Now we can get to the discussion of the main discussion topic, which is us trying to talk about envy free cake cutting, because that is what is stronger, that is nicer as well. It feels a lot nicer to get a piece of cake and thinking that everybody else got it equal or worse than me. I think we all relate to that. So as I previously said that we went over this case already once. So agent 1 cuts the cake, P1 P2, agent 2 chooses one of the cakes, either it is both of them are equal for them, so they can choose one of them, or otherwise one of them is more and the other one is less, they will take the more one. But for agent 1 it's both of the same, so they don't mind, they will take the other piece. That's it. Let's just talk about the envy freeness here once. So agent 2 gets their preferred piece, so by definition their piece is greater than or equal to the other piece, not envy, like no envy. And agent 1 knows that both of the pieces are exactly worth 1 by 2. So again, not envious at all. Now this is a bit of a big slide. So now that idea of simple cut and choose is not going to extend that well when you try to go to even 3 agents, because just think about it. You cut it into 3 pieces, then the second guy has to cut, because if he does not cut, if he just chooses the best, like the best piece he thinks, it is possible that the agent 3 also likes that piece a lot, and then they are envious of the other person. It is possible, say, that I cut the cake into 3 parts from agent 1's perspective. The agent 2 thinks, okay, so I like this so much that I value this piece to be 2 by 3 and the other to be 1 by 3, so I'll take this one, and agent 3 had the same valuation function, very possible. So then they would be envious of it, because the remainder is just 1 by 3 and that will also be divided, right? So that is why Selfridge and Conway came up with a algorithm or protocol in 1960, and this was in fact one of the, like, very few works of fair division. Fair division has been has had a lot of open problems and still does till this day, and that is this protocol about. So it's for 3 people. Now let's just discuss the steps. So agent 1 cuts the cake into 3 pieces. Okay, 3, 1 by 3, 1 by 3, 1 by 3. So P1, P2, P3. Now agent 2 evaluates the pieces, right? So now let us assume that they think that P1 is the biggest piece, right? So in that case they will take the knife and trim P1 down till it is perfectly matching their second favorite piece. So P1 is the best, then that must mean that there's second, which is P2, right? So they'll just match it to P2 and there will be a remainder R. So let us define the trimmed piece to be P1 star, leftovers to be R, and to agent 2 P1 star equal to P2 in value. Okay. Now agent 3 gets to choose, just get to choose. So they can choose any 3 pieces of the table. They do not get to choose the trimmings, that will be divided later, but they can choose the other 3 pieces. So P1 star, P2 and P3. Now they choose whichever one they find it to be the best. after which agent 2 chooses. Uh, now there is one rule they need to follow. If agent 3 did not pick this P1 star, then agent 2 must, with agent 1 taking the remaining untrimmed piece. Now the reasoning for that will be made clear. Just think about the situation after stage 1 of divisions once. So agent 3 was the first one to choose. They had all of the choices on the table, so they obviously chose the whatever is best for them, so they do not mind others' piece right now. We do not talk about R. R is still on the table. Everything about what everybody else has taken, they don't mind. They are fine with it. Now for agent 2, they got one of their top 2 choices. But if you remember, we made them to be equal. Remember, so we took it the second piece to be P2. That is what we assumed. So they had this and this. These were the 2 most favorite pieces, right? So that is exactly what we are forcing them to do, and therefore they do not really mind, right? If agent 3 chose P1 star, then they would get P2, like they can take P2. If agent 3 chose P2 or P3, they can just choose P1 star, no issues, right? And for agent 1, they just got an untrimmed piece, 1 by 3, already that is what we assumed in the first step, so there is no issue. With everybody else, just did trimming and all that, they don't really care. So they also are not envious. Now dividing up the trimmings is a bit more of a convoluted process, not too convoluted but slightly convoluted. Yeah. So basically now we are at stage 2, dividing the remainders. So either agent 2 or agent 3 picked up P1 star. That is what we had made them do.
Can you explain agent 1 situation also?
Sorry?
Agent 1 situation.
Oh, agent 1 situation, yeah. So if you notice, agent 3, what can they choose? P1 star, P2 and P3. They chose one of them. There are 2 cases. They chose P1 star, then agent 2 chooses P2, so agent 3 chooses P3. The agent 1 chooses P3. First case. Second case, say agent 3 chooses P3, then in that case we are forcing, or P2, whatever. So in that case we are forcing agent 2 to choose P1 star. So agent 1 ends up getting either P2 or P3, one of them. Now think about it. What we initially had done. We had done, okay, I have a cake, we split it according to agent 1's wishes, 1 by 3. That is what we did in the first step. So P1, P2, P3, all of them had the same value. And that is exactly what happened here. And that is why they don't mind, because everybody else either got 1 by 3 or they got less than that because it got trimmed. So now we just define this terminology. So what we shall be now covering is the major idea behind the Aziz Mackenzie algorithm, irrevocable advantage. So let's get started on that. So I have agent 2 or agent 3 taking the taking the trimmed piece P1 star, right? So let us call the person who took the trimmed piece to be receiver, the person who did not receiver, like non-receiver, sorry. Yeah. So now the non-receiver will be cutting R into 3 pieces, the value equally, right? That is what we are tasking them with. So it could be either 2 or 3, one of them. Now the agents will go as follows. The receiver will take it first, agent 1 will take it second, and non-receiver will take it third. Okay, that is how I am making it to be. So non-receiver cuts, non-receiver chooses last. Because otherwise, imagine them choosing first, then so they would just like cut it and get the best slice, they'll be done. Other people won't get their chance. What if they chose the best one for them, right? So they go last, and receiver and agent 1 alternate like that. Now let's talk about the envy of this situation. Okay. So the non-receiver cut into thirds with respect to the evaluation function and they got 1 piece. It's easy, they are not envious. Sorry? Oh yeah, sure. So did you understand receiver, non-receiver? Yeah. So now basically non-receiver, we are tasking them with cutting R into 3 pieces. So the person who did not take the trimmed piece. And then after that, since the non-receiver cut the cake, we'll want them to go last, obviously, because otherwise they go first or earlier than somebody else's nice cake might be taken away. So the receiver and the agent go. So the receiver, then the agent, then the non-receiver. The reason for the receiver going first will be explained. Like you will understand when we do the envy freeness part, right? So first of all, let's just deal with the non-receiver. Easy thing. They got 1/3 of their piece. They don't mind anything. They initially got that 1/3 thing, and now they got this. So they do not mind at all. They have no envy at all. Now receiver chose their favorite piece of art by choosing first. So what happened in the first case, they had no envy. In the second case as well, they got their favorite piece, so they also do not mind. However, for agent 1 it becomes a bit more convoluted, because exactly the thing is, if the receiver chose first, then shouldn't agent 1 be envious of their share? Possibly. So this is exactly where the idea of irrevocable advantage comes into play. Like again, this is written. So in the first stage, agent 1 got an untrimmed piece of cake, which was 1/3.
So do they think that the receiver initially got less than 1/3? So like
Yeah, that is exactly the idea. So initially the guy got 1/3 minus V1 R, and even if they take all of the remainder, then also it comes out to be 1/3. See, so like say they took the entire remainder, they did not give it them at all. They just like stole it all. So in that case, what would you get? These two would cancel. It would just be 1/3. This is equal to them. So why would he be envious? Right. So therefore, agent 1 does not envy the receiver due to this buffer. Like that is a major idea of irrevocable advantage. And in fact, we later on redefine this in the Aziz Mackenzie. Where is it? Yeah. So we redefine this in the idea of domination. So we just say that okay, I have AI to be a piece of cake currently held by agent I, and let R be the unallocated remainder of the cake sitting on the table. Then in that case, I would say that I dominates J if valuation of the cake of I that I has right now, so AI, is more than or equal to the remainder plus the allocation of J. So like if I see that I have some amount of cake and I know that you have some amount plus all of the remainder you take, even if and in that case if I have more than you still, I value it more than you still, then in that case I would say that I am dominating you. Okay. So before we get to that though, let's just talk about the problems with Conway's extension, like Selfridge Conway. So this was the protocol for n equals 3. Now n equals 4, it becomes a lot more convoluted, as you think, we do the same thing again. We have agent 1 cuts the cake into 4 equal pieces, agent 2, 3, 4 all look at the pieces. Suppose they all think P1 is the biggest, that is possible. So then agent 2 will trim P1 to P1 star to match the second favorite, creates a trimming T2. Agent 3 also trims P1 star, so it becomes P1 star star and creates trimmings T3. Okay, then agent 4 chooses and say they take an untrimmed piece, does not matter. But if you think about it, it becomes a lot more complicated to think about or follow about it more, because there's a lot of cases and sub cases in which you get stuck in. It's not a nice extension, right? So that is why n greater than equals 4, it is a problem for Selfridge Conway to follow. Now again, they do not hold any clear, well-defined, irrevocable advantage that they can use. So for that, Brams-Taylor protocol was established in 1995. However, the procedure is a bit too convoluted to state in this talk. I will not be going over it much. However, I will just be discussing few ideas from there, which is that it was the first finite envy-free cake cutting protocol for an arbitrary number of agents, and it extended the concept of irrevocable advantage, which was stated in Selfridge Conway. Yes. Oh, okay. So it basically, the essential thing was that it took the idea of domination and it just did that, okay, I'll take any arbitrary pair and I'll create an irrevocable advantage amongst all of them. Right, it would create amongst all of them, and then so if everybody has an irrevocable advantage over the other in a sense, then they can give the remainder piece to anybody. That was the main idea there. Now obviously, as you can think, it is a very complicated protocol and also a very lengthy protocol. Just think about it, n people, you have to do every single pair you have to balance, then you have to rebalance, and all of that meant that while it was a finite protocol, it was not necessarily a bounded protocol. Just to define the terms, finite protocol is basically guaranteed to eventually stop at some point of time. However, it is not going to going to run infinitely, but it can always determine if it will terminate or not. Like when we can terminate, we cannot bound it easily. Okay. A bounded protocol is just a protocol which is an upper bound. So a finite one is also, say, a bounded one is also going to be a finite one, basically. And the issue with the Brahms-Taylor protocol is this, that I have an agent 1 and an agent 2 evaluating a piece of cake, both of which are at a distance of, say, some epsilon, arbitrary epsilon. So the way they work is that I will be creating an irrevocable advantage, and the protocol will I will cut it so that after some point of time the remainder is basically stripped from to be less than epsilon. That is the main idea. So they will give a bit of this, give it a bit of that, and they will keep distributing such that after some point of time the value of remainder is less than epsilon. Alright. Now it takes a lot of steps. Again, it's a bit complicated, so it takes a lot of steps, and the number of cuts is essentially the value of remainder on the table right now divided by epsilon. So as this epsilon keeps decreasing, the number of cuts goes to infinity. So while the protocol stops, it's unbounded. It can take infinite, like a billion steps for 4 people. It is very possible, just depending on the epsilon you choose for the valuation, say, differences. The same piece I am evaluating to be, say, 0.5, and the other person is evaluating to be 0.5000001. That epsilon of 0.00001 is going to be the problem there, and it will cause a lot of cuts, which will be necessary for us to overcome this disagreement, which is why we come to the Aziz-Mackenzie theorem of 2016. This is the main crux. We first of all, as I said, we formalize domination. Did everybody get the idea of what domination means, or do you want me to re-explain that? You want me to re-explain? Okay. So again, say AI and AJ be the cakes allotted to I and J respectively. So then I would be set to dominate J if if according to I here, the value of AI is greater than equal to AJ plus the remainder of the cake on the table. So they can take all of the cake in the table, I don't mind, because I have gotten enough. I wouldn't mind that. They can take it. I will still have it either better or equal to them. It's fine. So that is what it would mean if agent I dominates agent J. Okay. Yeah. Like the thing is that when somebody dominates the other, the person who is dominating, that their perspective is taken in this case. In fact, we'll take it to be a graph. So we work with graph theory here a bit, which is introducing domination graph here. It is just a directed graph which has all of the vertices of being the agents, and the edge exists if I dominates J. So I comma J belongs to is an edge if I dominates agent J. The goal of this definition, which I don't think I wrote, is that what we want to eventually have is a complete graph. Complete graph, you might be a bit confused that it is a directed graph, so how would we have a complete graph? So what it would mean, let us just think about it with 2 agents in perspective. Okay, so see, I have 2 agents, 1 and 2. Okay, so I dominates J, 1 dominates 2 and 2 dominates 1. What does that mean? That according to I or 1 thinks that I have it better than J, even if they take the remainder, and even J thinks the same, that I have the better one if 2 thinks that they have the better one, 1 can take it all, they don't mind. So that is what it means, that if one dominates the other and the other also dominates one.
Okay, so when we are saying that agent I dominates agent J,
Hmm.
does that also has the assumption that the perspective we are looking at
Hmm.
from I?
Yeah.
And when I say agent J dominates agent I,
Hmm.
we will also assume that in J's perspective,
Yes.
J is dominating.
Absolutely, that is the thing. So the person who dominates, their perspective is taken, just like as you can see in history, that the winners always write the stories, right? So it is kind of like that. So the person, like the reason we have a domination graph is to, we want to eventually get a complete graph. That is what we want. Are you following? If you want, I can repeat. Okay, so basically a domination graph is a directed graph. All of the, like, you understand what domination means, right? Yeah. So all of the vertices are the agents, and I comma j belongs to, is an edge if I dominates j. Now previously, as I mentioned, that I dominates j, that means that with in i's perspective, I has it better than j, even if j takes all of the remainders, right? That is what it means, right? So VIAI is greater than equal to VIAJ and VIR. What does that mean? The valuation of AJ and all of the remainders. So it is greater than that, greater than or equal to. So domination graph is just that. And the reason we define it is because of the fact that we want a complete graph. Means, say I dominates J and J dominates I. Back. So how does that work? What does that mean? That means that I thinks that if J takes the remainder, I don't care. J also thinks if I takes the remainder, he also does not care. So neither of them care. You can give it to anybody. Both of them will be envy free. Yeah. So a complete graph would mean you have a remainder, you can just give it to anybody. Nobody cares. So the Aziz Mackenzie protocol, this is a bit of a complicated one, which is that it relies on two algorithms. Like, this is a simplified version, relies on two algorithms. The initial paper had like 5 particular protocols: permutation protocol, extension protocol, and all that. So simplifying them, it is 2 protocols. The first is the core protocol, which is the, like, nicest thing to work with, which is that, say I have a bunch of cake remaining on the table, and it goes over every single permutation of the n agents, and then allocates a certain portion to agents I and j. Like, it takes a permutation, and we'll later on prove mathematically that such a permutation will exist unless everybody has the same valuation functions, that I and j, they will have some sort of imbalance. Makes sense? So like one piece will have, and I and j will value it differently. So there will exist certain trimming of sorts that would guarantee an allocation so that I dominates j. Like, that is the way we will divide the remaining cake on the platter, and it will return the rest of the trimmings which is still left over. And the main protocol is just a very simple thing of running a loop of calling core protocol again and again and again until there are 2 cases. One is the cake just is over, there is nothing to do anymore, or the graph G is complete. That means that everybody is indifferent. Whatever remainder you have, you can give it anyway, nobody minds. Make sense? So let's just do the main protocol setup and all that first, then we can get to the crux. So I have the main protocol, which takes in the agents and the cake, and it initializes the allocation for every single agent to be phi, nothing, remainder to be cake, like entire cake, and the domination graph to be a phi graph. So basically, like, all of the sets are there, so all of the vertices are there, but no edges. Nobody dominates nobody. So now the first thing we'll do is we'll call the core protocol. This is the number of agents, the remainder of the cake, and the current graph. Then the core protocol will return a partial allocation of R, as I mentioned. So it will cut some part of the R, and it will split it among the people, and it will get some one domination it will get, right? And then after that there will be some trimmings remaining, which will be the R dashed. And because it is adding one domination at least, so it will add at least one new directed edge to G as well. Okay. So then we just need to check, like, first of all we'll update the state of remainder because it's a loop, right? We'll update the remainder to the new remainder, and then we'll say that if G is complete, then just divide the R anyways, just give it to anybody, nobody cares. and then we return the allocation after the loop is finished. So loop ends if G is complete or if R is 5. Okay, so like that is all of the cake has been distributed. Now then we have the core protocol, which is a tad more convoluted, which is basically that it takes an n agents, cake piece which is W, and current graph which is G, and it will output a partial NV free allocation of W. It will basically, again, it will just distribute the subsection or subset of W, and it will return the unallocated trimmings, right? And it will always add one directed edge.
What is a partial NV-free allocation?
So partial NV free allocation is just a bit more rigorous way of saying that if I have a cake, I am cutting it in such a way so that whereas some portion is like left over, but whatever rest I have, it will be the like nobody minds each other's. Like so if I say give cake to or some people and I don't give to other people, the overall collection of cakes I have, so say 1, 2, 3, 4, 5, 6, all of the agents who have, the current holdings are NV free. So at this moment, if at any point I run the core protocol, I'll have say I have agent I and agent J, they do not mind each other's portions. They are NV free of each other.
So the agents who get a piece of the cake do not mind each other.
Actually, nobody will mind initially. Initially also nobody minds. No, nobody gets nothing. Like everybody has 5. Then after that, the first allocation you do, you give everybody a bit so that everybody has something, and nobody is envious. Every single step of the way, there is no envy.
But how do we guarantee that such a
Permutation. Sorry.
how do we guarantee that such a allocation exists?
How do we guarantee that such a allocation exists? Yeah. So actually, there is this thing of yeah. So that is what, like, we have this permutation existence. That is what we discuss about later anyways, but I will just take it now. So let's say the existence of permutation in core protocol is not going to be guaranteed, right? It's not guaranteed, so we should try to prove it once. So here's a rough sketch. Like I have tried to simplify it as much as I could. I couldn't do it as like less than this. So I have, say, the agent 1 cutting the cake into n pieces, n equal pieces, and every single untrimmed piece is worth exactly 1 by n of W to agent 1. So equal pieces, right? So let us assume across n factorial permutations, no agent secures an advantage. That's exactly what we want, right? So if somebody got an advantage, then we would be able to distribute. So then for all permutations like pi, any permutation you take, then the margin between the untrimmed piece and the trimmed piece is strictly less than or equal to trimmings t pi, as in I have taken a trimming, right, which is t pi, whatever I am discarding away, and the margin between untrimmed and trimmed piece is going to be less than or equal to the trimmings. So now the major idea is that if the margin is always smaller than the trimmings for every single permutation, then t pi must be incredibly large for every single permutation. But if you remember one thing, that every trimming is cut from main pieces. So wait, why is it? Okay, now it's right. So basically the thing is that if I have agent 2 and agent 3 having different valuation functions, right? Agent 1 cut the cake, agent 2 and 3 say they have different valuation functions, then there must exist a piece where they disagree. Sorry. Yeah, so they disagree. So now I can take one permutation A where agent 2 trims before 3, and there I'll have a specific chunk shaved off, and the other one I'll have 3 trimming before 2, and there I'll have a different chunk shaved off because they have different valuation functions. Simple thing. So now the major idea that comes up here is that there is a major difference in the density functions. So then swapping the turn orders will always alter the physical size of trimmings, because otherwise the trimmings, if they stay the same, that means that I'm cutting this chunk and they are cutting that chunk, and it's basically just the trimmings are still the same. They just seem to be permuting, and that would be still a contradiction. You can yeah, exactly, like you can try to get an inequality and then you can disprove it. Like I am just saying that verbally mostly, because it is a lot of paperwork. So so now this was just difference in density functions, that the density, like the physical size of trimmings changes, and for over n permutation, n factorial permutation, every single combination of different densities are evaluated. So now a bit of a far-fetched application of pigeonhole principle, you will get that since the total volume of W is going to be less than or equal to 1, it is mathematically impossible for all of the trimmings to be always greater than all other margins for all the combinations using this property. So you will be able to, like, this is kind of like a sketch. So using this thing, you will be able to argue that for all combinations, if this is the case, then this less than or equal to 1 cannot hold. It will need to be infinite. And like the only other case, only case in which we do not have that issue is if all of the trims are equal, are identical, which means in that case I do not really need the core protocol anymore, because everybody has the same valuation function, because everybody has the same trims. No. So that is the main idea. Obviously I would have liked to been a bit more rigorous about the entire proof, however it is a tad non-trivial to write it and mention it in the talk, which is why I did not. If you like, I can like later on send that to you. Yeah. So I'll just finish the core protocol setup, and then we will be done with most of the talk. So the core protocol setup, as I mentioned, partial NV free allocation, basically, you remove the trimmings, everything else is allocated nicely. So first thing you do, equal cut, agent 1 cuts W into n equal pieces such that every single piece is 1 by nth of the total valuation. Now the permutation loop, what we do is we take the every single possible turn order of pi of agents 2 to n, and then they evaluate the pieces individually, and then each agent trims the favorite piece down to perfectly match the second favorite, exactly what we did in Selfridge Conway. And then we record this. So we save the tentative piece choices and the leftover trimmings T pi generated by the specific turn order. The first half of the algorithm. And the second half is that we try to find the margin. The math will basically guarantee, as I showed after this, is that it will guarantee that there will exist always one recorded permutation pi star where agent I takes an untrimmed piece, agent J will take a trimmed piece, then the value gap for agent I is strictly greater than Vi, Vi of this trim. Okay. And after that, what we do is we just allocate the pieces according to the choices in T. This particular permutation we got, we update this directed edge to G, because now I will dominate J, because this margin is strictly greater, right? So then in that case we return the remaining trimmings to the main protocol as the new remainder. With that context, is that a bit like more clear of what this proof kind of talks about? I think that helps a bit now, right? I'll just leave this page on for a few, for a bit, so that you guys can read. Let me know when to switch. It's not audible to. Yes. So we are iterating over all of the permutations. Actually, it comes from Sn minus 1 technically, because agent 1 goes first. So this particular pi we are talking about, we just chose one agent 1 though. So we can take any arbitrary agent, so it's technically just a bit of jargon there. And I think this is also a bit more clear then. I'll just leave it on for a bit as well. Okay. Now just one thing I would like to go over is how is this algorithm bounded, because as we have probably done in our algorithms courses, this just seems like an exponentially bad algorithm, right? Which it is. So I have n number of agents, E being the, let's try to just upper bound this, E be the maximum number, right? What am I saying? E be the number of missing directed edges in the domination graph, right? So the maximum number can be this, right? Because imagine it's a directed graph, so we want both ways. So there's no divided by 2 here. Is the maximum E, and we define this C and E to be the maximum number of cuts required to finish this protocol with N agents and E missing edges. Sorry? Divided by 2 is not there because I want a complete graph, both goes away. So I want I to j, j to I, 2 edges. So now you do the edge sum. You have n choose 2 times 2 because 2 edges. Done. So now this is just like I am just giving you a naive bounding, by the way. This is not an accurate by any sense. This is just to show that there exists a bound. So as to reduce E to E1, the core protocol has to run. We want to add one edge. That is what the core protocol does. So let us say that every single iteration of the core protocol reduces only one time. Worst case scenario, no. So then I cut the cake, check all n factorial permutations. For every single permutation, I will need to generate a pile of trimmings, for which the protocol will have to recursively call itself to divide these to ensure NV freeness. So there's this, it branches, then you have another branch, then you have another branch, and it goes a lot deep. Then the complexity to find therefore one edge involves branching n factorial many times, and in each branch doing work proportional to finding an edge in the next layer down. So n factorial many branches, n minus 1 factorial, so on. So then that means that we get a recurrence. We have C n E, which is less than equal to n factorial times n squared times C n E minus 1 whole to the power of n. Whole to the power of n because we need to go deep. We have a lot of branches, right? We go n to n minus 1, n minus 1 to n minus 2, n minus 2 to n minus 3, so on till 0. The last step is technically trivial, yes, but I'm still count that. And n factorial is also for the branching. What you want to ask something?
What is N square? N square.
Oh, this generation of trimmings. Every time you generate a trimming, you will need to evaluate for n people, no? So technically it should be n choose 2, but I just write that as n squared. So just a naive version of the upper bound will look like this. So I have the step 1 like this, I expand it. All of that expansion kind of approximately gives us a upper bound of this geometric series, right? E we can take to be maximum. This is an upper bound, so I am just taking approximation as long as it is greater than. Note that this is not the official one. The official one is a bit more lengthy, so I just came up with something by myself. So E max is n times n minus 1, approximately n squared. So this E n squared. So basically that is what will dominate. We can just say that n factorial times n squared whole to the power of n to the power of n squared. Very bad upper bound, not the one I promised, because that one was that had 5 protocols, too many things going on, too hard to cover in this talk. So I just came up with a simple one because, as I previously mentioned, FSTOC they went to this conference, they presented that paper, then after that they realized that they could actually flatten that recursion thing down to n to the power of n to the power of n. Before that it was n iterated to 6, which is the title of the talk. Now epilogue, why do we care? So the problem of fairly dividing continuous good over any number of agents was an open problem for 70 plus years, right? So this particular theorem, why it caught my interest was it was a very major theorem in the field of fair division, because it started off a lot of other inspired algorithms. If you think about it, the first algorithm, I cut you choose, okay, that was trivial, but after that Selfridge-Conway, what did that come up with? It came up with the idea of domination. Same thing used in Brahms-Taylor, but those people could not make it to be bounded. These people modified that a bit more, used some graph theory and came up to be, made that to be bounded. It was a horrible bound, but still bounded. Just like what mathematicians do, we just say that okay, this problem can be solved. Is it reasonable? No. I mean, 2 to the power of 2 to the power of 2 to the power of 2 to not nice, not nice at all. So it kind of also propelled the study of fair division. There's a lot of sub problems or variations of this problem. So you had redivided goods, We can also divide bads. So say an example actually of continuous batch I cannot really come up with at the moment. However, a discretized version of this would be chores. Say I have 10 chores, I want to I want everybody to take their own chores and all that. So that is what kind of propels this. Regardless, we'll just discuss some of the variations of the problem and then we'll be done. So there are a few other notions of fairness. We had defined two of them, proportionality and envy freeness. There is another one which is important, which is Pareto optimality, which basically says that okay, I have this particular allocation, it is the best allocation ever. There is no other better allocation than this of this particular piece of cake, right? Without making somebody being the loser. And equitability, it just says that which is the hardest one. It's very hard to satisfy. In arbitrary case, it's not even shown to be proven, which says that every agent receives exactly the same subjective value. So V1 A1, V2 A2, so on and so forth, Vn An, all of them are same. So everybody thinks that everybody thinks that their piece, whatever the valuation is, all of them have the same subjective valuation. Hard to achieve. As I said, alongside EF means envy freeness. Without a central omniscient referee, there should be a central fellow who is like, okay, I want to moderate this guy, because not everybody will share what they think or how they evaluate everything. And what about the bad stuff? It is just a minimization problem. But do note that we cannot just take the negatives of this value of the valuation functions, because remember we took it to be non-negative and we took it to be greater less than equal to 1. So there was this current breakthrough which I could find in 2018, which was envy-free chore division for an arbitrary number of agents, which was by these people. I'm going to try to pronounce Deghani, Farhadi, Haji Aghai, Yami, which modifies this algorithm a lot more and is also even worse in complexity, because it uses a lot of snapshots to take this negativity into account, because just assigning a negative value does not work. Lastly, we have the topic of finite divisibility, which is also a field of study and a lot more realistic in real life. So you can use it for a lot of stuff actually. So chore division, mass division, whatever. So an EF1, which basically just says that for any two agents I and J, if agent I envies agent J, then that envy can be eliminated by removing one single good from J's bundle. So I remove one from your tasks or your goods and I'm happy. That is what it says essentially, which is exactly this. Like some good you remove, I'm happy. And EFX, which is envy free up to any good, which means that if I envy you, I envies J, then the envy can be eliminated by removing any positively valued good. In that one, there existed one at least. It was guaranteed. In this one, any positive you remove, it works. That is EFX. A few things. EF1 can be solved using simple round robin selection. So 1 to n, all of the agents just keep going in a order. So 1, 2, 3, 4, 3, so on. N people choose. You keep continuing. Everybody chooses their favorite ones, and then you will be done. It will be EF1. It is a very simple problem to solve. However, for EFX, it is extremely hard to ascertain, and it was only recently proven that n equal to 2 and n equal to 3 cases exist. N equal to 2 had been proven, but n equal to 3 cases was done in 2020, 2023, something like that. And for chores, in fact, EFX allocations don't always exist even. It has been disproven for some cases. And with that, I would like to just state my references once. So I had the Handbook of Computational Social Choice, Chapter 13, by Brandt et al. And Discrete and Bounded Envy-Free Cake Cutting Protocol for n number of agents by H. Aziz and Mackenzie, Envy-Free Cake Cutting on Wikipedia, and the other research paper I mentioned, I think I forgot to add the link to that, by Yami et al. That is all for the talk. Hopefully I was able to explain all the concepts of fair division to you guys, and if you guys have any doubts, then please do ask. Any doubts? Okay, no doubts, fine then. Yes, thank you for the opportunity and have a good day.
So I hope you liked today's lecture, and thank you all.
Yes.